Thank you, and thanks to the organizers for a lovely conference and also for the opportunity to speak here today. So first I should mention that everything I'm going to be talking about is joint work with Alan Sola, who's in the audience, and James Pascoe, who's not, but who I think a lot of you all have met and who's located at the University of Florida. And so in particular, the three of us have been working on rational inner functions for several years now. So kind of this talk is going to be based on our third paper, which is about the structure of rational inner functions in more than 2 dimensions. But a lot of this is motivated by how rational inner functions behaved in the setting of the bidisk, so in the 2-variable setting, which is kind of what we discussed in our first 2 papers. And so I apologize to those of you who've heard me speak about this before for about the first half of my talk, even though I would like to get to the setting of more than 2 variables, really to motivate the sort of questions that I'm asking and the partial results that we get. I'm going to have to tell you the better situation in the setting of the bidisk. All right. So before I even get to the bidisk, I just want to remind you all what rational inner functions look like in the 1-variable setting, so on the unit disk. So on the unit disk, we know that the boundary is simply the unit circle, and it's very trivial to define what we mean by an inner function. These are functions that are holomorphic on the unit disk, and the radial boundary values have modulus 1 almost everywhere. And if we impose the additional condition that our functions be rational, well then we're looking at some of the building blocks of function theory on the unit disk. In particular, we only get the finite Blaschke products, which of course a number of people are talking about later on in this conference. And so once we look at finite Blaschke products, we see that, well, our rational inner functions are more or less completely determined by their collection of zeros inside the unit disk and the unimodular constant out front. But maybe more importantly, to extending this theory to higher dimensions, is that there's a really nice symmetry between the numerator of a finite Blaschke product and its denominator. Once you know the denominator, you can reproduce the numerator immediately. So I'm not going to talk very much about finite Blaschke products, but instead we've been interested in how do we generalize finite Blaschke products to the setting of the polydisk, so the d-dimensional setting, where, of course, by the polydisk, I mean the set of points where each coordinate separately has modulus less than 1. So one thing to notice here is that if you're on the polydisk, then the boundary is a lot more complicated, right? You certainly have the collection of points in the boundary where the modulus of every coordinate is equal to 1. This is the d-torus, and it's the distinguished boundary of the polydisk. But you have a lot of faces of the polydisk, so the collections of points where some of the coordinates are less than 1 and some of the coordinates are equal to 1. And for the majority of the time, I'll be talking about the d-torus, but there'll be certain aspects of my talk where we need to look at pieces of the boundary that correspond to faces of the polydisk. Well, if we care about defining functions that are inner, we use the distinguished boundary of the polydisk. So in particular, inner functions are holomorphic on the polydisk, and the radial boundary values as we go out to points on the d-torus have to have modulus equal to 1 almost everywhere. Now, if we care only about the inner functions that are also rational, well, they aren't going to look just like finite Blaschke products because, of course, if we have multivariable polynomials, we can't factor them into linear terms. But we still get a nice symmetry between the numerator and denominator. So what Rudin showed back in the 60s is that once we specify the degree of our rational inner function, so we say what its largest power is in z1 through zd, then it's basically uniquely determined by its denominator. So a rational inner function comes equipped with a denominator called a semi-stable polynomial that doesn't vanish on the polydisk. And then to get the numerator, we simply take that semi-stable polynomial, plug in the reflections of z1 through zd over the unit circle, so 1 over z1 bar up to 1 over zd bar, conjugate again so that you get a polynomial in the fractions 1 over z1 to 1 over zd. And then you multiply by the appropriate monomial to give you the right degree of your rational inner function. So rational inner functions, even in the polydisk setting, still have this nice symmetry between the numerator and denominator. So just for the purposes of having an example in mind, let's start with this polynomial p that's not vanishing on the bidisk. So in particular, clearly if I plug in z1 and z2 from the bidisk, p is not 0. And we can use this to construct a rational inner function, say of degree 1, 1. So in particular, we'll just follow that construction that I mentioned before. We take our denominator, plug in 1 over z1 bar and 1 over z2 bar and bar again to get the term in parentheses, and then multiply by the appropriate monomial to get a degree 1, 1 polynomial. And then if we take the ratio of these two, I get a very simple degree 1, 1 rational inner function of two variables. And so the point of this example is that all of a sudden we have different boundary behaviors. In particular, if we look at this, the denominator of this rational inner function vanishes at the point 1, 1. And so in particular, we have this point 1, 1 that's on the distinguished boundary of the bidisk, but where our rational inner function has a singularity. And this is something that we don't see in one variable, right? If you take a finite Blaschke product, they all extend analytically past the unit disk. So all of a sudden we have a singularity at a boundary point. Now these singularities always have to happen at the common zeros of the numerator and denominator. So if we're in this two variable setting, Bezout's theorem tells us that we can only have a finite number of these boundary singularities. And so really this is kind of the motivating question that we were looking at in two variables and then later on in d variables. In particular, how can these rational inner functions behave near their singularities? Because in some sense, they're very well structured. They look a lot like finite Blaschke products. But on the other hand, they have boundary singularities, which wasn't something that was seen in the one variable setting. So before I get into that question, I just want to mention a couple of reasons why we might want to care about rational inner functions, at least in the setting of two variables, because first I'd like to kind of highlight the results that we have in the two variable setting. Well, in his work with rational inner functions, Rudin back in the 60s again showed that every bounded analytic function on the bidisk can basically be locally uniformly approximated by rational inner functions, if you multiply them by appropriate constants. If you make the h-infinity norm of your function bounded by 1, so if you look at sure functions, then you can approximate locally uniformly by standard rational inner functions. That result actually extends to the polydisk as well. However, if, say, as in the context of this conference, you're interested in interpolation problems, then rational inner functions also play an important role. In particular, I think we're all familiar with the Nevin-Linne-Pick problem and the fact that it was solved on the bidisk back in the early 90s by Jim Agler. Now, one of the things that came out of his construction was that if you have a Nevin-Linne-Pick problem on the bidisk, so a collection of nodes on the bidisk and a collection of targets in the complex plane, and you're trying to find a function that's analytic on the bidisk and bounded by 1 that maps your targets or your nodes to your targets, then if this problem is solvable, it has a rational inner solution. So in particular, if we want to understand the solutions to interpolation problems, we really need to study the structure of these rational inner functions. So without further ado, I'd like to talk a little bit about what we were able to show in the two variable setting. And again, the motivating question is we have these rational inner functions, and we really just want to know how they behave near their singular points. And I should mention that kind of the work that I'm talking about is motivated both by work that Greg Neese did on some of the earlier structure of rational inner functions, and also on some work on more general boundary behaviors that was done by John McCarthy, Jim Agler, and then also James Pascoe on how analytic functions on the bidisk, if they're bounded, behave near their singular points. All right, so the main objects that we ended up being quite interested in were first the behavior of the partial derivatives of our rational inner functions. In particular, if a rational inner function has a singularity, the partial derivative is automatically going to be unbounded. And so we can't really ask how big the partial derivatives get in the sense of modulus, but instead we started to ask what integrability class are the partial derivatives in, as a measure of how singular our rational inner function is near a singular point. And in investigating this integrability question, we ended up looking at two pieces of information that were associated to the rational inner function. It turned out that the zero set ended up being particularly important, which of course makes sense because singularities have to occur at common zeros of the numerator and denominator. And so if we have a singularity, the zero set of our rational inner function is going to have to go through that singularity. And it turns out that these zero sets go through the singularities in fairly structured ways. Something else that ends up appearing is, well, if I have a rational inner function, I know that if we restrict it to the D torus, or in this case, the 2 torus, and it's unimodular there. And then if you look at the set of points that our rational inner function sends to these unimodular constants, so we have these curves of points on the 2 torus, those all have to go through the singular point as well. And so we can ask, how do these unimodular level sets approach these different singular points? All right, so let's focus first in on the zero set behavior and what we can get from this. So for the purposes of this discussion, I'm more or less going to assume that our rational inner function has a single singularity at the point 1, 1 on the boundary. This is not at all a required condition. It just makes the theorems and results a little bit easier to state. So kind of think about having this rational inner function right here. All right, so if our function has a single singularity at 1, 1, well, we can take any unimodular constant and plug it into the second coordinate and reduce to a one variable function. And this one variable function ends up being a finite Blaschke product that comes equipped with a set of zeros inside the unit disk. And so one thing that we were interested in studying is, well, if I take zeta 2 and send it towards 1, so towards the z2 coordinate of the singularity, one of these alphas, one of these zeros inside the disk, is going to have to tend to 1 as well, because the zero set has to be going towards the point 1, 1. And we can kind of study how that's happening. We can study how these z1 coordinates of the zero set tend to the singularity as the z2 coordinate tends to the singularity. And we basically measure that using this distance function. It's more or less measuring, so these points in the zero set are lying in the second face of the bidisk. The z1 coordinates are in the disk, and the z2 coordinates are in the torus. And we can more or less study how the zero set restricted to that face of the bidisk is approaching the singularity. Well, it turns out that there's a lot of structure there. So if we send z2 to 1, one of these alphas is going towards 1 as well. And in particular, this distance, the rate at which that alpha is tending to the unit disk, can be controlled by the distance between zeta 2 and 1, but we have to raise it to a positive even number, which we call the contact order. So this is more or less telling us how the zero set is approaching the singular point if we stay inside a particular face of the bidisk. All right. And it turns out that we can use this notion of contact order to completely characterize the derivative integrability of our rational inner functions. In particular, the partial derivative of our rational inner function with respect to the first variable is an LP if and only if p is less than 1 over the contact order plus 1. So in the setting of our favorite rational inner function, it's a fairly simple computation to show that the contact order is equal to 2. And so then its partial derivative is an LP if and only if p is less than 3/2. And similarly, for this more complicated rational inner function, the contact order is 4. And so it's an LP if and only if p is less than 5/4. And one can actually construct a whole family of rational inner functions that hit every possible even contact order. So really what's happening is that we always have LP integrability at least at 1. And then the smaller the contact order, the further our integrability interval extends beyond 1. The smallest contact order you can get is 2, so the furthest you can extend beyond 1 is 3/2. But as your contact order gets larger and larger, so as basically your zero set is approaching more and more tangentially, the integrability drops and gets closer and closer and closer to 1. Now, this more or less covered what we did in our some of the main results in our first paper, but there was a lingering question as to whether contact order was the same between the two variables. Because notice there was a choice that we made here, right? We were looking at how the zero set approached along one face of the bidisk. And of course we could have looked at how the zero set approached to singularity along the other face, and that would give a notion of Z2 contact order, which would govern the other partial derivatives integrability. And in order to kind of think about contact order in a new way, we switched to studying unimodular level sets. So you've seen two rational inner functions already, so this phi, which I have written on the board, and psi, which is given above. And really what I've done is graph some of their unimodular level sets here on the 2 torus. So I'm graphing them in terms of the angles associated to the point, so graphing from minus pi to pi on both coordinates. And so then our singularity that was originally at 1, 1 has been shifted to the origin 0, 0. But otherwise, each of these curves, so is something like C minus 1 or C1 or Ci, and these tell us all of the points that our rational inner function sends to that particular unimodular constant. And so we can see that all of these unimodular level sets go through the singular points, but they don't just go through kind of randomly, they go through with a lot of structure. And so we wanted to investigate the structure with which these unimodular level sets approach the singularity. And so in order to do that, we looked at these unimodular level sets and studied them for quite a bit, and were able to show that, unlike the zero set, you can actually parameterize these unimodular level sets using analytic functions. And so these curves are actually can all be parameterized using power series centered around Z2 equals 1. So even near the singularity, they're smooth. And then we can kind of study how close these unimodular level sets are bunching together. In particular, so in both of these pictures, each unimodular level set has one particular curve, but you could have a number of different components coming into the singularity. But if they just have each have one component, it's easy to see how to compute contact order. In particular, you take the 2 power series associated to, say, 2 unimodular level sets, you subtract them, and you take the power of the first non-vanishing term. So this gives you the maximal order of vanishing between the difference, and that power will always give you exactly the contact order. And so in particular, you can use the structure of unimodular level sets to compute this positive even integer that governed derivative integrability. One thing I should mention is that this method actually is reversible. If we do it, say, for Z1 and get a K1, we can basically invert many of our arguments to get a K2 for Z2 and show that the 2 contact orders have to be equal. And so what this implies is that the derivative integrability for the partial with respect to Z1 is same as the integrability for the partial derivative with respect to Z2. All right, so now I want to switch over to the polydisk setting. So here, again, we were governed by the same question. We have these rational inner functions with boundary singularities. How do these rational inner functions behave near them? And in order to see why the situation is a little bit different than the situation in 2 variables, let's look at 2 very simple examples. So basically here all I'm doing is taking the favorite rational inner function, the simple one here, and slightly modifying it to get a rational inner function in 3 variables. So in the first setting, I simply append a variable and increase this constant by 1. Well, if we look at where this function vanishes on the boundary of the tridisk, it only vanishes at the point 1, 1, 1. So we're basically in the same setting that we were in before, where we have a single singularity on the boundary of the tridisk. However, if we modify in a slightly different way, now this denominator here vanishes when Z3 is 1 and when Z1 times Z2 is equal to 1. And so all of a sudden our singular set is a curve on the boundary of the tridisk. And it turns out that this distinction matters. These different types of singularity sets impact the type of results we get when we say look at derivative integrability. Now, I should mention that if we're on the tridisk, these are more or less the 2 situations that we can have. So Adler-McCarthy and Stankus showed back in 2006 that the dimension of the singular set here is always going to be less than or equal to d minus 2. So when we were in the setting of the bidisk, we always got a 0-dimensional singularity set. If you're in the setting of the tridisk, we can have dimension 1 or dimension 0. But as the dimension of your polydisk increases, the dimension of your singular set can increase as well. So the problem gets kind of more and more complex as we go along. However, because of what we saw in 2 variables, we can try and ask similar questions in this 3 and higher variable setting. Can we say something about the derivative integrability of rational inner functions? Does this somehow connect to the zero set behavior or the behavior of their unimodular sets? In particular, is there some way that the zero sets are approaching the singularity that governs derivative integrability? And is there some way that the unimodular level sets are bunching together near singular points that again governs derivative integrability? Well, I first want to mention that kind of the initial integrability cutoff is the same as what we see in 2 variables. In particular, on the polydisk, we always know that the partial derivatives are at least in L1. And you can show this by basically doing the slicing argument that I mentioned before to get a finite Blaschke product. And then what we're more or less doing, if you look at L1, is studying the integrability of the derivative of a finite Blaschke product. And that's something that's fairly easy to work out in the L1 setting. And we can try and play the same game for p greater than 1 that we were doing in the 2 variable setting. In particular, we can try and slice to get a finite Blaschke product. And if we do that, we're going to have to fix a unimodular constant on the d-1 torus and plug it into our rational inner function to get a finite Blaschke product. If we do that, we again get a collection of zeros. As zeta hat tends to, as its coordinates tend to the coordinates of a singular point, one of those a's is going to have to tend to a point on the unit circle as well. And so we can study the rate at which that's happening using a similar distance function. And it turns out that just like in the 2 variable setting, the integrability of this distance function governs the integrability of the partial derivatives. So we can show that this partial derivative of our rational inner function is in LP if and only if, well, now we have a more complicated term here. If the integral of the distance function raised to this negative power over the d-1 torus is finite. And so this is more or less what we had in 2 variables. But in 2 variables, we also had the condition that that distance function, so in 2 variables, we knew that our d phi zeta hat was approximately 1 minus zeta 1 to the k1. And if you can plug that into if we were able to plug something like that into our integral, we would again get a condition like we saw in the 2 variable setting, right? In the 2 variable setting, plugging this in here for the distance function would give us integrability exactly when p is less than 1 over k1 plus 1. But the problem is that, well, I'll hide that for a moment. This distance function is significantly more complicated than what you see in the 2 variable setting. For example, in the 2 variable setting, if you're trying to understand the zero set of a polynomial, you can use Puisseau's series to write one coordinate of the zero set in terms of the other coordinate. So we at least know that there's a reasonably defined way to connect the coordinates of the zero set of your polynomial. Now, in the 3 variable setting, that's generally not true. There's a large literature about trying to resolve singularities in this type of situation. And we tried to work through some of that in this setting to get a better kind of notion of our distance function, but things are abstract enough that we couldn't get concrete formulas enough to really make progress on understanding the structure of this distance function. So that's one barrier. Another barrier is that even if this distance function is well defined and we can write it down, it doesn't need to be continuous. And it doesn't need to be the formula doesn't need to extend nicely to every point, especially when we have curves of singularities. The third problem is that even if the distance function is nice, so these are some examples of nice distance functions, they don't have to basically look like monomials. We can have lots of different polynomials showing up as our distance function. So these are some examples for rational inner functions that have singularities at 1, 1, 1. And so then what we're really trying to do is understand how our z3 coordinate is tending towards the unit circle as our zeta hats tend to 1, 1. And the distance function can look like a theta 1 squared plus a theta 2 squared, which gives integrability less than 2. It could also look like the product of those. So this is a higher degree polynomial, which gives integrability p less than 3/2. And both of these correspond to rational inner functions with a single singularity. It's not immediate kind of from what I've written here, but the rational inner functions we generated here kind of behave near the singularity like this rational inner function did. However, in these second two examples, our rational inner functions have a curve of singularities. And so here, we get a higher integrability cutoff, worse integrability, which means a lower integrability cutoff. But down here, we actually get the same as what we saw in our second rational inner function. And so the point is that there's kind of a lot going on here. We get polynomials of different degrees, and whether or not we have curves of singularities or finite singularities, and also the degree of the polynomial that we get, all seem to govern the integrability. In particular, we're somehow taking positive homogeneous polynomials that vanished at the origin and trying to integrate them with negative powers here. And there's not an immediate kind of structure in place where one could compute what those integrals should look like. I mean, certainly for low-degree polynomials like this we can, but we could also get distance functions that are homogeneous polynomials of degree 16. And then how do you determine, raising them to a negative power, what the right cutoff power is for that to be integrable? It's just a very hard question. So in order to try and pin down a little bit more about what was going on, we did a case study of very simple rational inner functions on the tridisk. So we can look at rational inner functions here of degree mn1, so the z3 only appears to power 1. And so then you can basically take your rational inner functions and break them into pieces that either involve a z3 or don't. So let's say we do this. And then this gets rid of the problem of trying to compute your distance function, trying to write the z3 coordinate of the 0 set in terms of z1 and z2, because you can do it automatically, right? So here's just an example of breaking up our polynomials. But if we're trying to compute this distance function, then because we can solve p tilde for z, set it equal to 0 and solve for z3, we get this fraction here automatically. I've replaced the tildes with the normal polynomials because on the 3 torus, they have all of the same moduli. So this is just a slightly easier distance function. But as long as p1 doesn't vanish, then this is a real analytic function that we can expand near zeta hat equals the 0.11. So we can chart to understand, or we at least know that our distance functions have to approximately look like polynomials near the 0.11. All right, so if we're in that setting, then we were able to say some things. In particular, if we were in the setting where our singular sets were finite dimensional, then we have an integrability cutoff. We know that our partial derivatives are not going to be integral for p greater than 2. And the p less than 2 situation can happen. So we get p less than 2 right here. And that comes from the rational inner function with denominator 3 minus z1 minus z2 minus z3. So kind of the obvious analog of our favorite rational inner function gives integrability up to 2. However, if our singular set has dimension 1, then there's some cutoff that's less than 2. In particular, we conjecture that the cutoff is 3/2, but we haven't actually been able to prove that yet. In particular, these partial derivatives are going to be integrable at least up until 1. There's some alpha between 1 and 2 where they have to stop. We think it's 3/2, and then they're not integrable past that. However, this condition here that the p1 not vanish is necessary for this theorem to be true. In particular, let's consider this simple polynomial right here that doesn't vanish on the tridisk that's built from a 2-variable rational inner function, in particular the one here. Well, its p1 certainly does vanish at 1, 1. And if you start to build its distance function, you end up getting that it's equal to just 1 minus 1/2 squared, so it's a constant function. So certainly the partial derivative with respect to z2 is an LP, for all p. But if you look at the z1 and the z2 partial derivatives, those are only integrable up to p equals 3/2. And so this is an easy example to work out, but it kind of illustrates that there are some complexities here in terms of how the variables interact that provide barriers to getting a comprehensive theory. Because this is a very simple situation, and there are just certain conditions that we have to make so that, so that basically all of our variables see the singularity. It's not immediate that, in this case, Z3 isn't going to see the singularity. It comes from the condition that P1 is 0. And so if we have much more complicated rational inner functions, it's hard to see exactly what all the conditions are that we need to impose so that we know whether certain variables see the singularity and certain ones don't. So that's one barrier. Now, in terms of understanding derivative integrability in two variables, we also looked at unimodular level sets, right? And in that situation, the unimodular level sets were always curves that met at the singularity, and how closely they met governed the derivative integrability, which of course makes a lot of sense because if the unimodular level curves are coming together very tightly, the function is changing values very rapidly, which would correspond to the derivative being very large. So we would kind of expect to see that type of behavior in the 3-variable and higher situation. And certainly we're seeing some of the behavior. Even in these higher dimensional settings, we do know that our unimodular level sets, which are now higher dimensional surfaces, always contain our singular sets, which can be curves or in higher dimension surfaces as well, at least in their closure. So that's what this says. We were able to show that these unimodular level sets contain our singular sets in their closure, so the question at least makes sense. We could try and investigate how these unimodular level surfaces bunch together at our singular curves and try and use that to measure integrability. Now, the problem is that our singular sets are no longer particularly nice. And so here's just an example to illustrate the problem. Here's a rational inner function. Its singular set is the red curve. Here. The gray surface is one of its unimodular level sets. So now I'm graphing on T3, so again, with respect to angles going between minus pi and pi. And you can see that part of its 0 set is this vertical line here at, well, there it's 0, 0, Z3, but we're graphing in terms of angles, so there's really a component of the singular set that's at 1, 1, Z3. Well, the problem is that our unimodular level surface has to contain that entire vertical line in its closure. And so it's a nice surface until it basically gets to that vertical line, and then it has to, basically Mathematica can't draw it. There's a huge singularity there. And then kind of the problem is that that's exactly where we would want to measure the bunching of the unimodular level surfaces because that's the worst behavior of the function, right? We would want to measure really where our two singular sets connect, but our unimodular level surfaces aren't even continuous there, much less analytic, so we can't try and measure the maximal order of vanishing in any way as, compared to what we did in the 2-variable setting. So we did look back at our case study to try and get a better understanding of what these unimodular level sets looked like, and it turns out that they were more or less governed by this polynomial here. So again, we're looking at rational inner functions that only involve a Z3 so that we can break their denominator into 2 components. Define, for each unimodular constant, lambda, we can define a polynomial Q lambda. And it turns out that just by looking at Q lambda, we can say what these unimodular level sets look like. In particular, just as in this picture here, the unimodular level sets are going to have to contain some collection of vertical lines. These vertical lines come from the places where that polynomial Q lambda vanishes. And then they're also going to contain some 3-dimensional surface. And the surface comes from, writing the Z3 variable as this function of, Z1 and Z2. And that function there is actually a 2-variable rational inner function. So if you look in the at least this specific 3-variable case, then our unimodular level sets are composed of vertical lines and graphs of 2-variable rational inner functions, which we know can have a bunch of singularities. So it's really not surprising that in this 3-variable setting, we're seeing that our unimodular level sets have a bunch of singularities. And so kind of interest to us is trying to understand the structure of these unimodular level sets in higher dimensions or kind of in more general situations. So I think more or less running out of time. I see a 3-minute sign, and so I'll just end with this slide. Here's basically what we can do at this point. We can start with very complicated rational linear functions, and we have various ways to determine what their zero sets are. So here's a complicated rational linear function. Its zero set is this collection of straight lines. And once we can pinpoint the zero set, you can often define what this distance function looks like. And the distance function will govern derivative integrability, and if it's not so complicated, we can say what the derivative integrability here, in this case it's p less than 3/2. And we can also then understand the unimodular level sets. Here the unimodular level set looks a little bit more complicated. In particular, it contains 2 vertical lines that come from the singularities of its defining 2-variable rational linear function. Notice those black lines are not part of the original singular set of the 3-variable rational linear function. Those are singularities that are connected to the unimodular level set itself, and those change depending upon which unimodular constant you pick. But we can look at kind of these structures in a number of specific cases, but currently don't have a way to kind of develop a general theory in 3 variables for kind of all of the reasons that I hit along the way. So I'll stop there.
I have to repeat the question so they can hear it and record it. So if I understood the question correctly, if the rational linear function has a limit that exists at the point?
It has a radial limit.
Has a radial limit.
And if the function is directionally differentiable at the singularity in any direction pointing into the polydisk.
Okay, so if it has a radial limit and it has a directional derivative pointing into the polydisk.
In any direction pointing into the...
In any direction, then
does the directional derivative exist?
Then does the directional derivative exist?
I think that we always have directional derivatives going into even the singular points, is at least my understanding. Well, certainly in the bidisk setting, right? We always have directional derivatives and we always have non-tangential limits at the singular points. In the polydisk setting, I thought that we did know that we always have directional, because they have modulus 1 and they have non-tangential limits that are unimodular at every point on the boundary of the or on the d-torus, kind of regardless of whether or not there's a singularity there. So I think that we have directional derivatives pointing in, regardless of whether or not we're at a singular point. Does that answer your question?
Yes.
Okay.
Are there other questions? Okay, then let's thank Kelly again for the talk.